Man must chart his own course as it improves the well-being of mankind.
For centuries, we have searched for meaning in existence, convinced that space and time define the limits of reality, that what we see is all there is. And then, the most chilling thought.
Whatever reality is, you don't see it.
Forces beyond the 4 dimensions we know shape everything. The expansion of the universe, the motion of galaxies, even time itself. But what if, beyond this, everything is different? This question takes us beyond science, beyond logic, to something deeper. Because here, we face the unthinkable. Since ancient times, humanity has struggled with the nature of the cosmos. The Babylonians charted the heavens with meticulous precision. They believed the sky to be a great dome over the earth. The Greeks considered the notion of multiple worlds. Philosopher Anaximander proposed that the cosmos was boundless, and that this universe was filled with infinite universes beyond our own. And in 9th century Iraq, philosopher Al-Kind introduced the idea of infinity beyond. The universe may extend beyond what we perceive, and hence, reality might not be confined to what is observable. Fast forward to this century, our understanding of the universe has expanded, quite literally. We all know that the cosmos is not static. It is growing and stretching outward at an increasing rate. Let's do a little experiment. If you look up at the night sky, you'll see a vast and seemingly infinite expanse of stars, planets, and galaxies. They all commonly stretch across a void, like this one, for example. The void's isolation makes it significant because it represents an extreme deviation from the large-scale structure of the universe. Is this just a statistical anomaly, or is there something deeper here? Anyway, let's not get sidetracked. As we've already covered in past Beyond Ideas episodes, this expansion of the universe was attributed to Edwin Hubble in the 1920s. It led to the realization that the universe had a beginning, a moment of expansion known as the Big Bang. And so the question becomes, what is causing this accelerated expansion?
Inflation is a twist on the Big Bang theory that attempts to describe what I sometimes refer to as the bang of the Big Bang, what it is that set the universe into this period of gigantic expansion.
For years, the leading explanation has been dark energy. It is an unseen force that makes up nearly 70% of the universe. I mean, if we think of the total energy density of the universe as a full chart, then 70% of it is dark energy, 25% is dark matter, and only 5% is ordinary matter, like the stuff we actually see in the visible universe. Now, what if dark energy isn't coming from within the universe, but is instead the effect of something outside pulling on it? Imagine a balloon expanding. The usual idea is that someone is blowing air into it, making it bigger and bigger. But what if instead an external force is stretching it, pulling on it from a dimension we cannot perceive?
If we, as a 4-dimensional spacetime, were embedded in a 5-dimensional membrane, then that 5th dimension, you could imagine that our 4-dimensional thing is expanding in the 5th dimensional thing.
That's Professor Charles Liu, the president of the Astronomical Society of New York. To make his concept more approachable, let's give it a fun twist. Now he's going to appear quite frequent in the following segment.
In order for that to happen, there are 2 assumptions you can make, and it depends, right? Assumption number 1 is, if that were the case, then that means that our observable universe is just a little bubble in a much larger universe, and something around the outside can therefore create that kind of expansion through suction.
If that's the case, our observable universe isn't an isolated system, but a bubble within a vastly larger reality. So the next question is, what lies beyond that? Another universe?
There are ideas, for example, something called eternal inflation, which suggests that might be a way that multiverse is created. But there's nothing that we know of in terms of the mechanics of the cosmology that we understand that could cause that in that scenario. If we, as a 4-dimensional spacetime, were embedded in a 5-dimensional membrane, then that 5th dimension, you could imagine that our 4-dimensional thing is expanding in the 5th dimensional thing.
One possibility is that our 4-dimensional spacetime is embedded in a 5-dimensional framework, and the expansion we see is simply the effect of forces acting in this higher dimensional space. Professor Liu provided a great analogy. It's like how an oil slick spreads across the surface of the water. It just keeps expanding no matter what. If this expansion is driven by surface tension, could we use that to travel, like a mosquito gliding across a pond?
If it is some kind of surface tension, that would be an awesome way to travel in the fifth dimension. That's because you're not in our four-dimensional space-time anymore. The laws of speed limits and physics or whatever, mass, etc., could be completely different.
This is actually one of the ideas proposed in the Randall-Sundrum theory by physicists Lisa Randall and Raman Sundrum. They suggested that if our space-time were connected to other four-dimensional space-times through membranes, it might help explain why gravity is so much weaker. Though we don't yet have the answers, these questions challenge our understanding of reality. What we see may not be the full picture, and that our universe could be just one part of something much bigger. As Carl Sagan so eloquently put it, the Earth is a very small stage in a vast arena. Then, there's another compelling idea about our existence, one that suggests reality isn't what we think it is. What we perceive may be nothing more than a simplified representation of something far more complex, a user interface of some sort, and it's designed not for truth, but for survival.
Whatever reality is, you don't see it. You see a user interface. My take is that reality, whatever it is always going to transcend any conceptual theory.
That's Donald Hoffman, a cognitive scientist and professor emeritus at the University of California, Irvine. In his book, The Case Against Reality, he presents a bold argument that space and time are not fundamental properties of existence. He even goes so far as to say that space-time is doomed.
Physicists are saying space-time is doomed. There's no such thing as space-time fundamentally in the laws of physics.
He put out a great analogy that really resonates with me. It is just like how a computer user sees an organized desktop. But we all know that at its core, the computer in front of us consists of raw electrical activity, circuits, and different voltages. So in the same way, our perception of reality may just be a front-end interface, and beyond that, a more complex nature of existence could be hidden.
In fact, the way I think about it is they're there to hide the truth because the truth is too complicated. It's just like if you're trying to, use your laptop to write an email, right? What you're doing is toggling voltages in the computer. But good luck trying to do it that way. The reason why we have a user interface is because we don't want to know that quote-unquote truth, the diodes and resistors and all that terrible hardware. If you had to know all that truth, it would, your friends wouldn't hear from you.
In other words, the world we experience like objects, colors, sounds, isn't reality itself, but a mere illusion shaped by evolution to help us survive. So if our perceptions don't reveal the true nature of reality, then what does? And what lies beyond this interface we rely on? To fully grasp this concept, let me bring you up to speed on the historical context. For centuries, deep thinkers believed that earth, air, fire, and water were the fundamental elements, that everything was thought to be composed of them. Then came the periodic table, which revealed a deeper truth, that these classical elements weren't fundamental at all. Earth, for instance, wasn't a single entity, but a mix of elements like silicon and iron. Then we went even deeper. Elementary particles like quarks, leptons, and gluons are the building blocks of the standard model of physics. And so the periodic table was great for chemistry, but it's not for uncovering the most basic structure of our reality. And now, we've explored the idea that space-time itself is doomed. According to Professor Hoffman, quarks, leptons, and gluons aren't the final answer. They're just representations of space-time symmetries. And so if space-time isn't fundamental, then everything we built on it is on very shaky ground.
When you get all the way down in that direction, what you've gotten down to is not fundamental reality, just the irreducible representations of a data structure. So you're always stuck inside the data structure, not to a deeper understanding of what's beyond space-time.
What we'll find is that as we step outside our little space-time bubble, we may encounter utterly alien forms of conscious experience, ones we might not even be able to comprehend. Think about it this way. If I asked you to imagine a color you've never seen before, what happens? Nothing, right? Your mind goes blank, and that's just one color. We know that some people already experience colors most of us never will. Researchers like Kimberly Jamieson have studied women with tetrachromacy. This is a rare condition where they have 4 color receptors instead of 3. Evidence suggests they perceive an entirely new dimension of color that the rest of us simply cannot imagine.
These women are apparently living in a world of color that no man can imagine them, and yet they're real color experiences.
Now take that concept further, infinitely further. Imagine forms of consciousness where every aspect of experiences is alien to us as a new color. These are possible varieties of conscious existence. They're real and yet completely beyond our understanding. There's one important key point that he brought up in the book, that perhaps we were shortchanged by evolution and lack the concepts needed to understand the relationship between brains and consciousness. Like cats can't do calculus and monkeys can't do quantum theory, so why assume that Homo sapiens can demystify consciousness? In his word, perhaps we don't need more data. Perhaps what we need is a mutation that lets us understand the data we have. Professor Hoffman really explored this radical departure from the conventional scientific view, which we all know it assumes that consciousness arises from matter. What he argues instead is that what we think of as physical reality emerges from a vast network of conscious agents, a sort of interacting systems of awareness that form the true foundation of existence. From this perspective, it becomes easier to see why debates about consciousness are so divided. Should we build our theories from the physical world up or from the mental world down?
The standard approach to consciousness is to figure out what complicated systems of matter with the right functional properties could possibly lead to the emergence of consciousness. Those who say, for example, that consciousness arises from orchestrated collapse of quantum states of microtubules in neurons. Or integrated information theory. Again, you start with something physical, and if it has the right kind of functional properties, then you have consciousness. You can be a panpsychist. You might say, in addition to particles in space and time, those particles are not just matter, they also could have, say, a unit of consciousness.
There are many, many theories about consciousness, and each of these offers a radically different answer to the same question. Today we're going to focus on 3 of the most well-known and widely debated. We'll start the first one with dualism. Imagine yourself sitting alone in a quiet room, thinking about a moment from your past. Maybe a conversation with your piano teacher, or the place where you met someone special in your life. The room is very much physical. You can touch the walls, feel the chair beneath you. But what about your thoughts? I mean, they're not made of wood or metal. They are intangible. This is the core idea behind dualism, the belief that the mind and body are separate entities. And your mind isn't just a collection of atoms, it's the ghost in the machine, a non-physical essence that merely uses the body as its vessel.
There are physical things, like tables and chairs and bodies, and there are mental things, like minds, people.
But dualism faced a major problem. If the mind and body are separate, then how does the mind control the physical world? Like when you decide to lift your hand, what actually makes your neurons fire? And that seems like a dead end. No one could provide a clear answer to this. Eventually, it became known as the interaction problem, and it's one of the biggest reasons people began to doubt dualism. Over time, the idea of a ghost in the machine lost ground, and a new way of thinking took its place. It's one that saw consciousness not as something beyond the physical, but as something built from it. Physicalism. If mind and matter are not separate, then perhaps the mind is just an illusion. So physicalism is the idea that consciousness is not some ghostly essence, but a mere byproduct of the brain.
Fundamentally, that's what reality is like. It's physics, physical particles, physical things.
Physicalists want you to think of your brain as a supercomputer. It processes information, fires neurons, and creates the experience of consciousness as a byproduct. There's nothing magical or mysterious about it. And so, since the universe is only matter, then consciousness is nothing more than matter rearranged, an emergent property of the brain. It's no more mysterious than fire emerging from wood. But here's where things get tricky. If consciousness is just a byproduct of the brain, why does it feel like something to be conscious? Why does red look red? Or perhaps coffee taste bitter? A computer processes information, but it doesn't experience it. A network of atoms shouldn't feel like anything at all, and yet here you are, feeling it. Physicalists had no answer. They argue that science will eventually explain how subjective experience arises from physical matter. But for now, the mystery remains unsolved. And so, physicalism and dualism have dominated the debate, but other theories attempt to blend the best insights from both. This one alternative idea seeks a kind of philosophical middle ground. It's panpsychism. The premise of this is very simple. If the brain is made of atoms and consciousness emerges from the brain, then perhaps atoms themselves are conscious. So panpsychists subscribe to the idea that consciousness is not something that emerges as a feature of complex systems, but something that exists everywhere, a fundamental property of the universe, just like mass or charge.
It doesn't literally mean everything is conscious, but the smallest constituents that the book or the socks are made up of have incredibly simple forms of experience.
The complex consciousness we experience as humans is just a more sophisticated expression of a universal property. So you need to think of consciousness as an ocean, and that each particle, no matter how small, contains a drop of awareness. But that doesn't mean panpsychists have all the answers. They too face significant challenges. One specifically is the combination problem. How do these tiny drops of awareness combine to form the unified experience we call consciousness?
Our conscious experiences seem smooth and unified and homogeneous. When you have a visual experience, it looks perfectly smooth. So how can you derive this smooth conscious experience from little bits of proto-consciousness? So that's the combination problem.
These questions remain open, yet panpsychism presents a compelling middle ground between dualism's mind-body divide and physicalism's purely physical view. And it raises a profound possibility. If consciousness is a fundamental property of the universe, could that mean the universe itself is conscious? That it thinks, dreams, and perhaps even reflects on its own existence? Sounds pretty peculiar, doesn't it? The idea that consciousness might be woven into the fabric of reality itself. Yet in our everyday lives, we navigate the world through tangible means. Like you need eyes to perceive visible light, ears to detect sound waves, and so every interaction with the universe is filtered through a practical interface. But there was a time when physics wasn't about equations and measurements. It was more of a metaphysical pursuit, a philosophical attempt to grasp the nature of existence itself.
Now, linking the universe with some sort of metaphysics is something that has been done since the very beginning, until such time as there was a true separation between empirical science and metaphysics. It was called natural philosophy, until people like Galileo said, you know what, I don't think we should really mix how beautiful is a tree or how righteous is a star. Let's just talk about the tree and the star and then worry about the philosophy separately.
In fact, Newton's most famous book, Principia, wasn't just about physics. It was formally titled Mathematical Principles of Natural Philosophy. This reflects an era when exploring the laws of nature wasn't separate from philosophical aspect. But philosophy didn't just shape the foundations of science. It also shaped how we think. It's in our nature to search for meaning and try to find patterns. We spend our lives anticipating the future. Back a few thousand years ago, it was really about predicting where the lion will move so we can run the other way. Nowadays, it's more like predicting when the stock market will go up so we can invest. Have you ever dreamed of making a slam dunk in a basketball game, and then a few days later you have the exact same experience happen in real life?
The brain is a prediction generator. So could it have been that your brain, in its generation of predictions, which dreams to some extent are, right, go on and had so many predictions in your lifetime, just that one random one came true just by chance?
Apparently, we humans adjust our memories backward. Every time we remember something, our brain recreates the memory. But sometimes people end up misremembering, not on purpose or to lie, but simply because their brain has actually shifted what they thought was really from the past.
Your brain set it up so that thinking back to the dream, it wound up matching the two pieces and getting them confused. It is possible.
But what if these patterns aren't just tricks of the mind? All we have to do is look at the little clues around us. We see repeating patterns. A river delta mirrors the veins of a leaf. The way neurons connect in the brain resembles the filaments of a cosmic web. Even the spiral of a galaxy echoes the structure of an atom. It's as if nature keeps using the same blueprint, scaling it up and down from the microscopic to the infinity of the cosmos. Scientists call these patterns fractals, self-replicating structures that appear at every level of reality. Some theories, like asymptotically safe gravity, suggest that they might be fundamental to how the universe operates. Are these patterns merely the byproducts of physics, or do they hint at an underlying code? If that's the case, then the universe didn't just create us as passive observers. It created us to look back at it. and perhaps to one day see beyond the code itself. Even from our tiny place in the universe, the way we figure out the bigger picture is always the same. We look for patterns, we connect pieces of data, and use them to imagine what lies beyond our perception. Whether it's astronomers mapping distant galaxies, or you trying to solve a tricky puzzle, it all comes down to the same process, turning scattered clues into understanding. So how do we get better at that skill? That's why we're partnering with Brilliant for this video. It's a platform that helps you sharpen your thinking every day with thousands of hands-on lessons in math, science, programming, data analysis, and AI. Like this one, for example. How would you even find the middle 50% of values here? It simply means finding the middle chunk of all the values. Imagine all the data points lined up from smallest to largest. Now mark the spot where a quarter of them are smaller. That's your left line. Then mark the spot where a quarter of them are bigger. That's your right line. The space in between is the middle half of the data. Slide the lines until they match those spots, and there you go. While you're learning practical things like this, you're also training your brain to think more clearly, logically, and creatively. Start your journey today with brilliant.org/beyondideas for a 30-day free trial. Just click the link on the screen or scan the QR code here. You'll get 20% off an annual subscription and begin training yourselves to recognize all the deeper patterns. Now back to that hidden code we talked about. If it's really there, why can't we see it directly? Professor Hoffman offers one fundamental answer, that what we perceive is only a user interface, a simplified version of reality designed for survival and not truth.
There are an infinite number of directions in which you can go infinitely far in more and more complicated consciousnesses.
And beyond the limits of space-time, he claims, we find structures. Astonishing structures. Geometric entities like the amplituhedron, fusion simplices, and what he metaphorically calls obelisks.
So we've been looking outside of space-time for 10 years, and what do we find? What you take off that, what's the obelisks? Geometric structures sitting there. Here I am. Could be millions of dimensions, it could be trillions of dimensions, they're just sitting there.
Or, if we take it to the extreme, this is what might exist outside the interface we call space-time. And that is just the beginning. So let's delve deeper into today's topic. Donald Hoffman once posed a deceptively simple question. Do we see reality as it is? The question points to something deeper, perhaps a sign that one of our core assumptions might be wrong, and that fixing this assumption might finally help us understand the nature of reality. Now, some skeptics suggest we may never solve this mystery, that perhaps our brains just aren't built for it, like monkeys trying to solve quantum mechanics. But Professor Hoffman is more optimistic here. If our brain is the device we use to interpret reality, then perhaps it's time we study the brain itself. And all this starts with neuroscience. Neuroscientists tell us that a third of our brain's cortex is dedicated to vision. Just opening your eyes activates billions of neurons and trillions of synapses.
Well, neuroscientists tell us that they're creating, in real time, all the shapes, objects, colors, and motions that we see. It feels like we're just taking a snapshot of this room the way it is, but in fact, we're constructing everything that we see.
But here's the twist. Vision isn't like a camera. Yes, your eye has a lens. It works like a 130 megapixel sensor. But your brain isn't recording reality. It's constructing it. You don't construct the whole world at once. You construct only what you need and when you need it. If you're still not sure whether the perception he's talking about can be trusted, well, let's try a few visual illusions. Here's the first picture. There's actually no triangle, but your brain is inventing it to make sense of the negative space. The second one. This static image appears to move if you stare at it long enough. And so motion is an artifact of your brain's refresh cycle. And the last one, perhaps the most interesting of all. which of the tiles is darker, A or B? You might think it's A, but actually, they're the same shade of gray. Your brain compensates for lighting, even when it's wrong. Speaking of color, did you know that color simply does not exist in nature? That green in the grass, blue in the sky, and golden hue in gold, if you zoom in close enough, down to the atomic scale, you'll find that color simply isn't there. At the level of individual gold atoms, there's no visible goldenness to them, just arrangements of protons, neutrons, and electrons. No color pigments, no shimmer. So then, where does it actually come from? Well, it turns out what we call color is just our brain's interpretation of different wavelengths of electromagnetic radiation. We all know about the visible spectrum we learned in high school: violet, indigo, blue, green, yellow, orange, and red. They're just a narrow slice of wavelengths our eyes evolved to detect. When light with a certain wavelength hits the retina, it triggers a cascade of electrical signals, and then the brain does the rest. It labels those with an internal experience, like red, green, or blue. And so that experience doesn't come from the atoms, it comes from us, constructed entirely in our mind. So if there's an alien species hovering above Earth, their red might not be anything like our red. In fact, if their wavelength spectrum extends far beyond ours, they might see things in your kitchen that appear completely invisible to you. Like when you heat up a bowl of soup in a microwave, they might perceive a glowing radiation of energy coming from within. So the only conclusion left is that what we see, even something as basic as color, is not a direct reflection of external reality. It's a construct, a custom interface built by your brain.
So what evolution gave us was perceptions that guide adaptive behavior, and part of that process, it turns out, means hiding the truth and giving you eye candy. Our space-time, 3 dimensions of space, 1 dimension of time, is a fairly trivial headset.
That sounds interesting. Why are we only equipped with senses to comprehend 3 spatial dimensions and 1 temporal? Why not 6 or 7 spatial dimensions? Or why not double timelines running in parallel? And these connections between events that we perceive as time are actually just part of the fabric of reality.
What could time be if it's not the way we experience it? What could it be pointing to? Time and causality appear to us the way they do because for whatever reason, we're only perceiving one moment at a time.
Later in this video, we'll explore what perception could look like if we were built to comprehend extra dimensions, other than the ones you're familiar with.
Even though time would be an illusion and the causality in the way we experience it is an illusion, it's still pointing to a deeper structure. There's something that it corresponds to in the fundamental nature of reality, that our perceptions map onto something. It's just not the experience of it that we're having.
And so this line of thinking leads to a compelling possibility that the reality we experience might not be the original structure. It might just be a projection, a simplified version of something more fundamental, something that is rendered into a format we can comprehend. And if that's true, then we should ask, is there anything in nature, any physical phenomenon that works exactly like that? Anything at all? Where a lower dimensional surface encodes a higher dimensional reality? As it turns out, there is something called the black hole's holographic principle. The concept is actually quite intuitive. Without diving too deep into the math of theoretical physics, the holographic principle suggests that everything inside a region of space, whether a black hole or potentially the entire universe, can be described by information stored on a lower dimensional boundary. This idea originally came from a puzzle in black hole thermodynamics proposed by Jacob Bekenstein and Stephen Hawking. They found that a black hole's entropy is proportional to the surface area of its event horizon, not its volume. The larger the surface area, the more entropy it contains. And as we all know, entropy is one of the metrics used to measure the information content of an object. And so, this led to a provocative conclusion. Everything that falls into a black hole might not be lost inside, but instead, its entire informational content is encoded on the surface, just like a 2D hologram that stores a 3D image.
It is possible mathematically to encode information about three-dimensional systems on two-dimensional surfaces, of how all the information on the one hand could be on the horizon of the black hole.
The idea that all of reality could be contained in 2 dimensions, and there's something about the interaction between different points that cause this holograph, so that it seems like there's a 3-dimensional world when in fact that it's a projection of this 2-dimensional surface.
In simple terms, everything that happens in a 3D space can be fully described by information stored on a 2D surface. And so, going back to the idea that our reality might be a projection, what if everything we experience is actually embedded in a lower dimensional representation within a higher dimensional structure? Something like a brain in string theory terms.
Once we let go of our massively intuitive but massively false assumption about the nature of reality, it opens up new ways to think about life's greatest mystery. I bet that reality will end up turning out to be more fascinating and unexpected than we'd ever imagined.
What he proposed was nothing short of remarkable. Space and time are part of the headset, a user interface that hides the true nature of reality. We don't see reality as it is. We see what we need to survive. So then, the real question is, if you could step outside of space and time, outside of the projection, what kind of structure would you encounter? Let's explore this in depth, coming up next, right after this. According to an article written by Professor Hoffman and colleagues titled Fusions of Consciousness, he proposes something pretty bold, that consciousness is the foundational fabric of reality. Not space, not time, and not matter. The entire physical universe emerges from the complex web of interactions among conscious agents. So, Professor Hoffman says that we should stop treating physical objects like particles and atoms as if they're the most basic ingredients of reality. Instead, what is fundamental is how things change and the probabilistic structure of those changes. So rather than asking what is reality, he asks, how do states evolve from one to another? And this is where something called Markov processes come in. They're basically the simplest model we have to describe probabilistic change over time. A Markov kernel, for instance, tells you, given that I'm in state A, what's the probability I move to state B? Let's say that you're a very simple creature with only 2 possible states of mind, calm and alert. Every moment, your state might stay the same or switch with some probability. That behavior can be described with a matrix like this. If x equals 0.9, you stay calm 90% of the time. And if y equals 0.3, when you're alert, you go back to calm 30% of the time. So this matrix Q is a single point inside a bigger mathematical object called the polytopes M2, which is the set of all such 2x2 stochastic matrices. But it doesn't stop here. Since this whole fusion of consciousness is really about dynamic systems and change, so what happens is that Hoffman introduces a dynamic law, something called kernel flow. In kernel flow, the values of x and y evolve over time, depending on how far they are from the fusion line, this line right here, a condition where the 2 states become fused, aka 2 experiences blending into one. This red path shows how this transition matrix evolves under the proposed dynamics. And so your calm and alert agent flows toward a new behavior, possibly one where the 2 states become indistinguishable. Now, what if you have 3 states instead of 2? Well, in that case, the projections of these marker polytopes would look something like this in 3D space. So here's the key idea. When you collect all possible n by n stochastic matrices, you get a geometric object, a polytope living in a high-dimensional space. Each point inside this polytope is a valid world of transitions, and its shape encodes how systems can evolve over time. In fact, with just a little bit of a Python script, we can visualize how these Markov polytopes would look like in 3D space. And so you can think of this as the area where reality lives, just like how physicists use space-time as the arena for matter and energy. So the bold claim here is that Professor Hoffman argues that this space, the space of kernels, transitions, and fusions, is more fundamental than space-time. This brings us back to the bigger picture, that beyond our conventional understanding of space and time, there might be a deeper realm composed of intricate geometric structures, structures that Professor Hoffman metaphorically refers to as obelisks. Things like the amplituhedron, tetrahedrons, fusion simplices, and so on. A kind of structure that is not situated within space-time, but exists outside of it entirely. And this, as he claims it, represents a deeper level of reality. And yeah, maybe the objects don't intrigue you for one bit, but what if we can just let our imaginations run wild and see all these shapes that exist outside of space-time, being imagined by none other than the power of artificial intelligence? So here's what it looks like. Now we're getting into one of the more mind-bending consequences that Professor Hoffman briefly mentioned. The idea that this whole structure of reality might stretch out in an infinite hierarchy of consciousness.
There are an infinite number of directions in which you can go infinitely far. Think about it like the Twitterverse. There are millions of users and billions of tweets. There's no way that anybody could read all the tweets or interact with all the users. So we have to have something to make it understandable. What we'd like to have is some kind of like headset that allows us to see what's happening in Wisconsin versus Tokyo or whatever. And that's what space-time is. It's just a little headset.
So what does that actually mean? I think it's best if we bring it down to something more relatable, like the Twitterverse analogy, or as we should probably call it now, the Xverse. So imagine yourself as Alex, 27 years old, living in Bergen, Norway. You're sitting in a coffee shop, just about to head to work, and you post a photo of your cappuccino. That's it. Your moment, your state of mind. In that instant, your experience is just that one picture, that one post, your 3 spatial dimensions, and 1 slice of time. That's all you've got. Now, let's add a little bit of a twist. What if you could also experience life as Brenda, someone else entirely living in Palo Alto? While Alex is winding down for bed, Brenda is just waking up, posting a picture of her jasmine tea. And now imagine that you, somehow, are both of them, seeing both posts, both timelines, all at once. I mean, you're not just switching back and forth between perspectives. You are simultaneously holding both streams of experience, 2 different spacetimes, inside one field of consciousness. According to Professor Hoffman, that's what happens when 2 conscious agents combine. They don't cancel each other out. They fuse into a more complex agent, one that contains and integrates both. Now, what if we take that crazy idea and push it even further? What if it's not just Alex and Brenda anymore? Like you're not fusing 2 consciousnesses, but hundreds, thousands, maybe even all of them. What does it feel like to be the entire Xverse? Well, you'd be perceiving every post, every thought, and every photo from the day the platform launched in 2006 up to now in 2025. You're not just looking at the feed, you are the feed. You're a 70-year-old veteran in Maine, United States, and at the same time, a third-generation Vietnamese revolutionary in Hanoi. You're a Maasai elder in Kenya tending cattle at dawn, and a K-pop fan in Seoul live-streaming a concert. So every shared image, every comment, every fleeting moment, all inside one unified stream of experience. That's what it might mean to scale consciousness upward. You're not one person navigating a network. You are the network.
Consciousness, what it's up to is exploring all of its potentialities. And the reason it's continuing to do that is because there's no end to it in principle.
And that's where this idea starts to resonate with something else, a short story called The Egg. I guess some of you may have heard of it. In the story, a soul is told that it has lived, or will live, every single human life that's ever existed. You're not just one person, you're everyone. You're both Genghis Khan conquering Europe and the little kid in Mongolia centuries later reading about him in a schoolbook. You're a Nazi soldier in 1940s Poland, pulling the trigger on a Jewish father in front of his family. And then, you're that father's son who survives and emigrates to Israel, whose grandchild, now a third-generation Israeli, joins the military and fires into a street in Gaza. But you're also the kid in that little Gazan alley, not understanding why the bullet hits your stomach. All of it, somehow, is you.
The entire life of Hoffman is one trivial perspective on who I really am. And each one of the billions of human beings is an important, but compared to the whole, trivial perspective on what the consciousness is.
And maybe this isn't just a story. Our whole discussion today suggests that it could be part of the deeper structure, that consciousnesses can scale, fuse, and span across what we thought were separate lives. If that's true, then at some point when you die, when the headset finally lifts, you see the whole thing. If reality is built on patterns of change in a realm beyond space and time, then what is that realm made of? What if mathematics itself began revealing patterns that didn't just describe our reality, but was the very structure of reality itself? Now, in order to test that, let's bring up one hypothetical case. The year is 2125. An artificial signal is received from deep space. Upon analysis from the European Southern Observatory, it was discovered that the narrow-band signal originated from the direction of Messier 87 and persists for exactly 7.4 seconds. Its structure is unintelligible at first, but when processed through a quantum computing system, the signal resolves into a sequence, 5009, 5011, and 5021, and so on, which the computer quickly realizes that it's a sequence of prime numbers. And so it begins. More primes follow.
You meet an alien species. They come to Earth. Do you know about prime numbers? They don't know the language. They think about what do you mean by this word prime? You start tapping out like 2 taps, 3 taps, 5 taps. You do that. The alien species has done like any thinking at all. They'll be like, I got such a natural sequence.
That's right. Prime numbers are not culturally defined. They are mathematically fundamental, divisible only by 1 and themselves. And so any intelligent system with access to basic arithmetic would eventually identify them.
And that's where we are. We've taken off the headset. There's these obelisks sitting there smiling at us. Quiet.
I mean, if alien life with no shared history, biology, or context uses the same mathematical constructs, doesn't that imply that mathematics is universal? And what about the notion that math was thought of as a human invention, created to solve specific problems on Earth? I mean, that's exactly how it was used. People assigned numbers to objects, like 1 sheep, then 2, 3, and all the way to 48. But now imagine what happens when the objects disappear. If there are no sheep, no herd, no context, and no observer to count, my question to you is 48 an objective fact embedded in our reality? Or does it only emerge when intelligence is present to define it? And so, if 2 hypothetical intelligences recognize the same concept of prime numbers. What does that lead to in our understanding of modern physics? Early mathematics had no abstraction. Numbers were attached to physical things. There was no concept of two in isolation, only 2 goats, 2 baskets, and 2 bricks. In ancient Babylonia, astronomers calculated lunar cycles using base 60 arithmetic. Their goal wasn't to understand the cosmos. They needed calendars for agriculture and civil planning. In ancient Egypt, geometry was developed to remeasure farmland lost by the Nile's floods. It wasn't until later that abstraction emerged. Greek mathematicians introduced formal proof and deductive reasoning. Indian scholars developed zero and positional notation, and these all became fundamental to the mathematics we use today. But here's the million-dollar question. If math started as a human tool, why does it work so well in describing nature? Why do tools designed to measure grain quantities end up describing planetary orbits, quantum behavior, or black holes in modern science? I mean, if math was made for Earth, then why does it describe the universe at the same time?
Mathematics allows us to take all of the complexity of the universe and wrap it up neatly into an equation or a system of equations that we can then understand and model.
If you're skeptical about the claim that math reveals something deeper, let's look at a practical case. The first one is E, Euler's number. Might look like just another constant. But let me tell you this, if you put 10 chocolates into 10 boxes at random, what are the chances that one of them ends up in the correct box? Surprisingly, that probability is very close to 1 over E, 36.79%. This isn't how E was originally derived. The constant comes from calculus and exponential growth. The probability connection came much later. Now let's look at the next number, pi. This one is different because it was discovered through empirical observation. Around 2,000 years ago, Babylonian mathematicians estimated pi using the circumference of a hexagon inscribed in a circle. Later on, during Archimedes' time, he used more refined polygons to approximate pi more accurately. He kept increasing the number of sides, getting closer and closer to a circle, essentially doing calculus logic centuries before it was formalized. And we fast forward to 16th century Europe, and we get the invention of the imaginary number I, the square root of -1. It was so bizarre that people at the time thought the number existed only outside the realm of tangible reality. So why even bother thinking about it, let alone inventing it? Well, it turns out, through robust mathematical derivation, that if we take all these E, pi, and I, they form this beautiful equation. E to the power of pi I plus 1 equals 0. The Euler's identity.
I mean, one of the things that people often look to in beauty is the simplicity. So if you look at E equals MC squared, so when a few concepts come together, that's why the Euler identity is often considered the most beautiful equation in mathematics.
In 1604, Galileo performed an experiment that demonstrated that the universe follows mathematical laws. He designed an apparatus that showed this clearly. So here's what happened. He wanted to find the relationship between distance and time, so he used a ramp, a ball, and some form of time measurement. He used arbitrary units, like 1 Galileo, 2 Galileo, 3 Galileo, and so on. The distance the ball traveled in 1 Galileo was recorded as 1 unit, so we've gone 1 unit of time, 1 unit of distance. Now, if he tried 2 units of time, the ball didn't travel twice the distance, it traveled 4 units. So he thought, this relationship is not linear. Then he tried 3 units of time and got 9 units of distance. So at that point, it became clear. The distance the ball travels is directly proportional to the square of the time. The relationship between distance and time was mathematical. And it holds up. And this part really blew my mind. You can test this experiment anywhere, on a hill, on Mount Everest, on Mars, or on the moon. The result remains just as valid today.
If necessary, at the end, to translate what you figured out into English, into a world, into the blocks of copper and glass that you're going to do the experiments with to find out if whether the consequences are true.
So in other words, we'd expect math to be so precise in describing the physical world, because sometimes it's the generalization of what is happening. And our physical reality is just a special case of this generalization, where we are constrained to a certain degree with something.
I think people often find it puzzling that something abstract like mathematics could really describe reality as we understand it. The best you can do is to describe some mathematical structure. You say there things that satisfy the Dirac equation or something like that, which you can't understand what that means without mathematics.
That's exactly what happens with Einstein in the general theory of relativity. He wanted to come up with an unconventional idea that gravity isn't a force, but the curvature of space and time itself. So he needed to expand the matrix. Einstein realized that Newton's laws couldn't explain how gravity works in accelerating frames, or under extreme conditions, like near a black hole, so he needed a new framework. But these equations appeared to not exist in physics yet, although they were already prevalent in math, and that's where Bernhard Riemann comes in. He gave a famous lecture in 1854 called On the Hypotheses Which Lie at the Foundations of Geometry, where he proposed that space could be curved, which, if you ask me, was an idea way ahead of his time. Riemann developed the metric and curvature tensor. The very structure he had envisioned turned out to be exactly what Einstein needed, and in 1915, Einstein finally published the general theory of relativity. It remains one of the most beautiful examples of mathematics predicting physics long before the theory existed.
If you say, I have a three-dimensional space, ordinary space, I want to talk about ordinary space, three-dimensional space, and you begin to ask them about theorems. Then they say, now look, if you had a space of n dimensions, then here are the theorems. Well, I say, yeah, but I only want the case 3. Well, substitute n equals 3. And then it turns out that very many of the complicated theorems they have are much simpler because it happens to be a special case. And later on, it always turns out that the poor physicist has to come back and says, excuse me, when you wanted to tell me about the 4th dimension.
It's clear that mathematics operates in the abstract, and through that abstraction, it allows us to describe hidden structures that help us understand the world. So let's walk through an example. This next bit was adapted from a famous TED Talk by mathematician Roger Antonsen. I highly recommend watching the full presentation of his. Anyway, we start with a two-dimensional shape, 4 triangles arranged in a 4-3 pattern. Now let's fold them together to create a 3-dimensional object. The result is a square pyramid. And let's just take 2 of these square pyramids and join them. That way we get a new shape called an octahedron, which is one of the 5 Platonic solids. And you might recognize it from our previous video featuring Professor Donald Hoffman. We'll return to that in a moment. Now, once we have this shape, we can rotate it along different axes and observe it from various angles. And each time, it looks slightly different, even though it's the same geometrical object, because what we're seeing here are the 2D projections of a 3D structure. This is the same principle we explored in the constrained hyperspace video last year. And we can do it one more time, and the more perspectives we explore, the more we learn. Each shift reveals something new about the same underlying object, just because we change our perspective.
I can use this as a tool for creating understanding. I can take 2 of these and just put them together like this and see what happens. And it looks a little bit like the octahedron. Have a look at it. If I spin it around like this, what happens? Well, if you take 2 of these, join them together and spin it around, there's your octahedron. Again, a beautiful structure. If you lay it out flat on the floor, this is the octahedron. This is the graph structure of an octahedron.
Let's pause here for a second. Remember this structure? It closely resembles the geometric forms proposed by Don Hoffman, the ones he suggests exist outside of space-time. In his concept, these forms represent a kind of consciousness that is more fundamental than space-time itself. They exist beyond our perceptual reach and are silently staring at us.
Geometric structures, not a dynamics, just sitting there. Here I am. Could be millions of dimensions, it could be trillions of dimensions.
So you might be wondering, how do 2 different researchers, each exploring the nature of reality through mathematics, arrive at similar shapes and structures? One is using math to examine perspective and dimensionality, while the other is using it to describe consciousness as a pre-spacetime entity. This overlap is too difficult to ignore. It's exactly identical to what we discussed at the beginning of this video, the hypothetical discovery 2125, where future humans detect a prime number sequence sent by an extraterrestrial civilization, a civilization with no shared language with us on planet Earth, no common sensory frame, and no shared numerical concept, yet somehow conveying something familiar that is mathematics. Here's my own realization while writing the script for this episode. Mathematics may not just describe the universe. It may be the substrate it runs on. And more specifically, in this universe, everything that exists and follows the same physical laws seems to align with the same underlying mathematical structure. That's why our math appears consistent, even across different minds. And so throwing this same apparatus, like Galileo's device before, this time on planet Kepler 16b, would essentially yield the same equations, assuming the same physical laws apply to both systems.
Let's have a mathematically precise theory of consciousness that starts as simple as possible. And then we have to boot up what we call space-time and the physical world as conscious experiences within conscious agents that they're using as an interface, a simplifying interface to help them interact with other conscious agents.
Roger Penrose, in his 1989 book, The Emperor's New Mind, argued that no machine could replicate human consciousness. This view runs counter to the ordinary beliefs at the time. Marvin Minsky, who many figures regard as the father of artificial intelligence, claimed that the brain is just a computer made of meat. What Penrose described was that it's not about how complex these machines are, or how fast they are, but rather that they were fundamentally limited by algorithmic logic. And that is something that human thought appears to bypass. And so, in order to fully explain this, Roger Penrose turned to quantum physics. He proposed that consciousness might arise from non-deterministic quantum-level processes, the kind of computation that goes beyond neural architectures. It wasn't long until Penrose collaborated with Stuart Hameroff. He introduced the idea that quantum coherence might occur inside the brain's microtubules. This is cylindrical protein structures within neurons. Their purpose is to regulate the shape and division of cells. But in this context, Hameroff believed they might also serve as biological quantum devices, the perfect candidates for sustaining quantum coherence. So together, Penrose and Hameroff proposed the orchestrated objective reduction theory. According to this, consciousness arises from orchestrated collapses of quantum states within these microtubules. Each collapse, or reduction, is not just a physical event, but a discrete moment of conscious experience, and they are internally driven by thresholds of gravitational self-energy.
That's what the brain does. That's what the microtubules do. Orchestrates the objective reduction. Hence the theory is orchestrated objective reduction.
Physicist Max Tegmark dismissed this idea on physical grounds. He argued that quantum coherence in a biological environment like the brain would decohere in less than 10 to the minus 13 seconds, far too quickly to have any cognitive relevance. Tegmark's conclusion was that if the brain were using quantum processes, we'd need to be thinking 10 trillion thoughts per second for it to matter. But despite this, in 2013, experimental results from a Japanese team detected vibrations in microtubules. If quantum activity could persist in microtubules for longer durations, then the biological conditions for Roger's theory might be plausible after all. This concept also touches on the debate around free will. Classical neuroscience suggests determinism, that all thoughts and decisions are caused by prior brain states. Roger Penrose challenges this claim. He argues that quantum indeterminacy could introduce genuine unpredictability into neural processes and disrupt strict causal chains, not through randomness, but through non-computable structure. This would create space for choices that are neither deterministic nor algorithmic. Okay, it seems that I've been talking a lot of gibberish English, but what does this all mean? How do you make sense of this piece of information? Well, the bigger consequence of this idea is that consciousness is not merely a byproduct of physical law. It may be fundamental to the existence of the universe itself. In Roger Penrose's words, somehow our consciousness is the reason the universe is here. It's almost the same message as Don Hoffman, who also thought that what is fundamental is consciousness. Although his idea is a little bit different in terms of how he explains the link to the physical world.
My assumption is that the fundamental reality is just consciousness. When we have different, for example, spaces and times, one organism has 10 dimensions of color perception, another one has 4, we have 3. Some organisms see in 4 dimensions or 2 dimensions.
If consciousness depends on quantum laws, and quantum behavior follows mathematical structure, then awareness itself may be grounded in mathematics. So if that's the case, then mathematics is not just a language we use to describe the universe. It may be the operating system the universe runs on. And what if we extend this thought process even further? What if there's an idea that describes not only that mathematics is the operating system, but that the very fact that our universe is mathematical? And so we're going to explore this in the last chapter of this video. Physicist Eugene Wigner once published an article, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. The statement pointed to a genuine epistemological puzzle. Why is it that equations invented by humans to solve local problems end up predicting phenomena far outside their original domain? This question is really the core hypothesis of Max Tegmark. He proposes what he calls the mathematical universe hypothesis, the idea that the universe is mathematics, not merely described by math, but made of it. In his view, every structure that exists physically corresponds to a mathematical structure.
I mean in plain English that our universe doesn't just have some mathematical properties, but that it fundamentally has only mathematical properties.
And this is the reason for the bit we showcased at the beginning of this video. A prime number remains prime, whether observed by a human, an alien, or an algorithm, because math at its core does not depend on language or culture. If it can be defined by relations, symmetries, and axioms, then it is a candidate for physical existence. And so this view extends the legacy of Plato's mathematical realism. The mathematical forms in Plato's ontology, like perfect circles, numbers, geometric solids, exist in a timeless and non-physical realm. They are not invented, but discovered by conscious beings. What Max Tegmark hypothesizes is something more radical, that the Platonic realm and physical reality are the same thing. Our universe is not embedded in math. It is math.
The reason math has been so effective in describing the world is that the world is mathematical, completely mathematical. We actually inhabit a mathematical structure. The approximations we've found so far are just some simpler math approximating, the actual math.
And so constants of nature like the fine structure constant, gravitational or Planck's constant, are not set by anything. They are intrinsic properties of the mathematical structure we happen to inhabit. And what we call physical laws are just features of that structure. But remember, it's only the reality we inhabit, not anywhere else. Only the space-time we know and love. And so if there's another structure or reality out there, this might not be the case. The Galileo experiment we showcased earlier might not yield the same relationship. Perhaps it could be another variable that is not time squared. Or the prime number would be another concept entirely. And all of this subset of mathematical structures would be classified into the level 4 multiverse by Max Tegmark, where it encompasses every single one of these subsets. And our reality now is just one point in an infinite mathematical landscape. So if Tegmark is correct, then consciousness, particles, space-time, and all physical phenomena are emergent aspects of the underlying math. The brain is a mathematical object, the observer is a mathematical process, and existence itself is formal, not material. It's a position that pushes the boundary of what science can empirically address, that maybe the simplest explanation is that our physical reality is mathematics in motion. Astrophysicists are sexy.